Dear all, good morning. I am Dr. V. Malati, Associate Professor, EC Department, SR University, Warangal. Today, this lecture is on machine instructions and programs. In this video, we are going to see memory locations and addresses, memory operations, instruction and instruction sequencing, then stacks, subroutines, and additional instructions. So first, memory locations and addresses. So here the number, the characters. Characters means operands. Operands are the data on which the operation is to be performed. I think operation means in the coding we will give commands. Those commands will be applicable on the data. That data will be known as operands, and instructions all are stored in the memory of a computer. So for any data to be operated upon, or whatever the instruction or information we need, definitely they have to be stored in any of the memory locations. Those memory locations are available in computer. And then memory consists of so many number of cells, that is in terms of millions of cells, each of which can store. So every cell can store one bit of information. One bit of information means either 1 or 0. Then because of this single bit, it represents a small amount of information. Suppose we want to have a big task to get it done, then this much of 1 bit storage element is not sufficient. So therefore we need to resolve this problem. And how to do? So first, a single bit represents a small amount of information. The usual approach is to deal with them in group of fixed size. So fixed size means we have to make each and every cell, the number of cells are made into a group. So later we will see a group of array, the array of memory cells. So memory cells are arranged in the form of matrix or arrays. So this is altogether called as memory locations. And then the memory is organized so that a group of n bit. So n bit means a word. So the word length is equal to n. How many bits? That is depending upon the architecture of the system. So this word can be stored to retrieve in single operation, or retrieved in single operation. So the general form of a memory word, and this diagram is taken from the reference book, I mean that is the Computer Organization amateur book, and this is the architecture of the memory cell, how a bit can be stored. So this one is n bit word. So in one memory location, n bit word, that is one word, can be stored. And since it is like a stack one over the other, the memory locations are stored or kept. That is, they are accomplished in the manner of one over the other. And then one over the another locations, the memory word, the words are stored. So how it is stored? The first one is first word and then second word. So after this, in between it is ith word and then it is last word. So from the bottom, from the top to bottom, the words are stored. So from the bottom to top, it is not being stored. From the top to bottom. So first one is first word, and so on it is moving. And then modern computers have word length from 16 to 64 bits. So in the previous slide we have seen n bit word, that n is not mentioned what value is. So n can vary from 16 to 64 bits. If the word length is 32 bit, that means one word is having 32 bit, then a single word can store a 32 bit to complement number or 4 ASCII characters each 8 bits. And this bit is the word is of, the word will store either signed value or unsigned value. If it is unsigned value, then it is 2's complement. It should store the 2's complement number. If suppose A to B, that is A to Z, alphabetic letters, then those words will be converted into ASCII character, and each will be of having 8 bits, and the storage manner is explained in this diagram. So here it is a word, that is 32-bit word. The bit starts from LSB to MSB. B0, bit 1, bit 0, bit 1, and B0, B1, B2, from up to B30, B31. It is not 32 because the counter starts from 0, so up to 31. And then the single bit, that is B31, is equal to, because normally in microcontrollers or microprocessors, the MSB, the first, this one is LSB and this one is MSB. So this MSB is the this number represents the sign of the number. So that is why this MSB, it is MSB. MSB is the sign bit always in microcontroller or microprocessor. MSB bit shows the sign of the whole number. So suppose B31 is equal to 0, then it indicates that the number is positive number. If it is 1, it indicates that it is negative number. And then ASCII character. For that, how it is stored? Normally, this 32-bit word is split into 4. So first one 8-bit, then 16, and then 24 bits, and then 32 bits. These 32 bits are divided into 4, each having 8 bit. So ASCII character 1, 2, 3, 4. Suppose if you want to store good, so GOOD, good. So GOOD. Otherwise GOOD. That depends on the architecture, how the architecture is created. Based on that, GOOD stored from left to right or right to left. Okay, so this one is the encoded information in a 32-bit word. This is diagrammatically explained. And next one, yeah, memory unit consists of data lines, the address selection lines and control lines that specify the direction of transfer. So normally, why we are specifying the direction of transfer means the data can be transferred from memory to processor for performing the task. Otherwise, processor 2 memory for storing the results after execution. And then number of address line equal to k. If 2 means there is a probability of 0 or 1. So two address lines, they can access 4 data. How it is 4 data? If we have 0 and 1 2 bits, with this 2 bits we can create 4 number of addresses. What are they? So 0 0 0 0 0 0 1 and 1 0 1 1. How I have created? Already I told you that we have only 2 bits, 0 and 1. So if you take the first bit is 0 0 and second bit is 1, with this we can create 0 0 0 1. Okay, and then with the second bit 1. So 1 1 means the second bit, maybe the probability of having the second bit is either 0 or 1. So in this way we have developed 4 locations. So if we give the option of 0 and 1 for creating addresses, we can develop 4 locations, namely 0 0 0 1 1 0 1 1. So number of memory word equal to 2 power k. So this is address lines only. So address lines k means how many number of words we can develop, we can process, we can use is equal to 2 power k. And then already we know word length is equal to n, and this n varying from 16 to 32. That also we know. So simply based on these points, we can use the diagram. This is the memory unit. So 2 power k number of words already we know. And n bit word length is n bit for one word. So next one, it is data lines. See the direction bidirectional, because data can flow from memory to processor or processor to memory. That is why from memory unit the data flow direction is bidirection. And then so anyway, any word is to be taken from the memory unit, definitely the address of the location of the particular word should be given. That is what k address lines. So address of the data will be sent in this line. And then next one, there are two lines, read and write. So read means there are two operations. So the data will be stored in the memory location, but that data is taken out, or in that memory location some other data is to be written. So in this way there are two types of operations. Number one, read. So read means the particular data will be read, and write means the based on this address line, the particular location into which the data will be written into. So these two lines are used to indicate the operation, which operation is to be performed on the particular memory word, the address of which is given through the k address lines. And next one, data lines provide the information to be stored in memory. So in the data is to be stored in memory. That is right. And then the control input specify the direction of transfer. So So depending on the read or write operation, the control input will indicate the direction of the data. And then, for example, a memory with 64 kilobyte words, 64k words, and a word size of 1 byte, then this memory unit has 64 into. So 1 kilobyte, normally 1k means 1000 we will tell, but in this case we should not tell 1000, it is 1024. 1k means 1024. So 64 into 1024, it is equal to 65,536 memory locations. So these many locations can be available. The address of these locations varies from, already I told you that the count should start from 0 to 65,535. So in general, so every time we cannot calculate some, if possible we can keep it in mind. Kilobyte is equal to 2 power 10 in terms of 2 power 10, which is equal to 1024 bytes. And megabyte, so 1 megabyte equal to 2 power 20, which is equal to, so this these many number of bytes. And gigabytes, so gigabytes equal to 2 power 30, terabytes 2 power 40 bytes. So normally kilobytes we will use, so 2 power 10 equal to 1024 bytes we will make it in mind. And next one, so byte addressability. So how we are mentioning the address, that is called as byte addressability. Successive addresses refer to successive byte location in the memory. Already we saw in the first diagram itself. The words are stored first, second, third. Like that we have stored. So the memory location address starts from here. Zeroth location, first location, second location, and so on. If the word length is 32 bits, successive words are located at addresses 0, 4, 8 and so on. Now you can ask, why not 0, 1, 2 and so on. Already to store ASCII character, we have seen one diagram, 8-bit ASCII first one and second one ASCII, second one 8-bit ASCII, fourth one 8-bit ASCII. So in this way 32 is split into 888. That is why here 0, so for here it is 0, 1, 2, 3, and then 4, 5, 6, 7, and then 8, 9, 10, 11, and then 12, 13, 14, 15. So 0 to 16 in this way. So here 0, 4, 8, and so on. Okay. So 32 means it will extend up to 32. Now I am telling 0 to 3, 4 to 7, 8 to 13, and 14 to 14, 15, 16, 17, up to that. Sorry, 8, 8, 9, 10, 11, 12, 13, 14, 15, like that. Next one, there are two types of byte addressable memory locations. Number one, big Indian and then little Indian assignments. So big Indian means, example, it will be used in IBM, Motorola, and HP, Hewlett Packard. And a higher order byte stored in the lowest address. That means byte 0, byte 1, byte 2, byte 3. So in the previous I told you example good. GOOD means GOOD, otherwise GOOD, like that. So in this direction or in this direction. There are two ways of representing the number or word. So in this that two ways are called as big Indian and little Indian assignments. So big Indian means how it will be from lowest to highest. Otherwise, higher order byte stored in the lowest. Uh, in case of 16-bit data, aligned words begin at byte addresses 0, 2, 4. In case of 32-bit word, aligned words begin at byte addresses because 32, that is why 0, 4, 8. So 64 means it is 0, 8, so the difference in the number of locations for storing one word is here 8, but here 4, here 2. So the difference is shown for different. The difference in two word will be different for 16-bit, 32-bit, 64-bit. In some cases, words can start at an arbitrary byte address also. Then we say that word locations are unaligned. Normally, there should be uniform difference between the two words. If it is not uniform, then it can be called as unaligned locations. So in this big Indian assignment, so big Indian assignment, how they have given 0, 1, 2, 3. So lower byte is in the first one. Normally we are using little Indian assignment because LSB here, MSB here, LSB here, MSB here. But in big Indian, LSB here, MSB here. So that is the difference. So big Indian means 0, 1, 2, 3, 4, 5, 6, 7 up to last one. So if k number of bits means 2 power k minus 1, minus 3, minus 2 and then minus 1. So in this way it is formed. And next one, little Indian. So here LSB, here MSB. So default we are using this little Indian only. LSB here, MSB here. 0, 1, 2, 3 and then 4, 5, 6, 7. So if you want to store good, GOOD. But in big Indian, GOOD. That is what the difference between the two. So a little Indian where it is used DEC and Intel. Lower order byte at lowest addresses. So byte 0, 1, 2, 3 like that. The order is changed. Next one. So for this, several examples are given. So example 1, a computer has 32 megabyte of memory. How many bits are needed to address any single byte in memory? So this is the question and then solution. The memory address space is 32 megabyte or this 32 megabyte will be 2 power 25. How it is split? 2 power 5 into 2 power 20. So numerator, powers can be added. So 25 is split into 2 power 5 and 2 power 20. And 32 megabyte already we have seen in the previous table. It is 2 power 25. And we need log 2 of 2 power 25. So log 2 to cancel. So finally we get 25 bits to address each byte. And example 2, a computer has 128 megabyte of memory. Each word in this computer is 8 bytes. How many bits are needed to address any single word in memory? So in the like the previous problem, this 128 megabyte it is equal to 2 power 27. So 2 power 27 means 2 power 7 into 2 power 20. However, each word is 8 bit, 8 bit and which means that we have 2 power 28, 24 words. So 2 power 24 means we need log 2 power 24. So log 2 cancelled. Finally we get 24 bits to address each word. So So here we got 25 bits, here we get 24 bits. So how to split in terms of 2 powers? That is the matter here. So here 2 power 25, here 2 power 24, that's all. And then next example, how many address inputs are required to access 256 bytes memory? So here the memory size is 2 power 256 bytes. So here 2 power k, and what is the value of k we should find out. So 2 power k is equal to 256 is equal to 2 power 8. So 2 power 8 means it is equal to 26. If you put 8 times 2, it will after multiplication you will get 2 power 256. So k is equal to 8 bits. It is very simple to calculate. In the same way, how many address lines are required to access 16 kilobyte of memory size? So 16 kilobyte means we know that 2 power 4 is equal to 16. 2 into 2, 2 into 2, 4. 8, then 16. So 2 power 4. So k equal to 4. But here it is bytes. But here kilobytes. So 1 kilobyte equal to 2 power 10. Already we have seen 1024 2 power 10. Already we got 2 power k equal to 2 power 4. So powers can be added 4 plus 10, 14. So k equal to 14 bits. And then both next one, memory operations. So here previously we have, up to this we have seen the memory addresses, and now memory operations. Because in the first basic diagram we have seen write line and read line. So based on that we have to see the operations. Both program instruction and data operands are stored in memory. So any instruction, I mean instruction means commands or program, or the data on which the commands are to be operated, everything, all data required for the program is also stored in the memory. To execute an instruction, the processor control circuits must cause the word containing the instruction to be transferred from memory to the processor. So read means from memory to processor. Write means from processor to memory. That is the difference. So that the difference means that is the direction of data flow. Operands and results must also be moved between the memory and the processor. Thus, two basic operations involving the memory are needed, namely load. So, read is ultimately called as load operation, and then fetch or store. So, fetch and load or read, or fetch, load or read or fetch, and store or write. Store means we are putting the data into permanently. Permanently means up to whenever the data is to be changed for the next command, up to that time the data will be stored. So stored means we are going to write the data into. So store means it is write operation. Load means we are loading the data, we are giving the data, that is load or read operation. Okay. The load operation transfers a copy of the contents of a specific memory location to the processor. So load means we have to give the data or copy the data to the from the memory location. So memory location means the address will be given, that is different, already we have seen. So based on the memory address, the controller will go to the particular memory location and take the data and give to the processor. The memory contents remain unchanged. Only thing for operation, the data is given. but in that memory location the content will never be changed because it is taking only, we are copying only. For our necessity we are reading the data, that's all. So the content will never be changed. To start a load operation, the processor sends the, so load operation, okay, but the processor, how it knows that it is load operation? For that, the processor sends the address of the desired memory location and requests that its contents to be read, and then memory reads the data because already address is sent, reads the data stored at that address and sends to the processor. So read means the main point to be noted here is the data will not be changed. Only thing, we are acquiring the data for operation. Next one. So diagrammatically how it is done. First one, memory data register. MDR means memory data register. MER, memory address register. So here we are assuming that memory data register contains a value of hexadecimal 3DH, and memory address register, now the pointer shows the 2003. So here memory, it is 2001, 2002, 2003. Already we have seen the location starts from 0, 1, 2, 3 like this. So word 0, word 1, word 2 like this. So in the same way 2001, 2002, 2003. Here 4B, 5C, 3K. So it is originally available. That is before execution. Now we are going to apply the operation. What operation? Memory read operation. Already I told you that memory read operation means the contents of the memory location will not be changed. The same thing is happened after completion of the read operation. See, we need 2003 memory location to data. In 2003, we are having 3K. So this 3K is given to the memory data register. Okay. So next one, memory write operation. So memory write operation, in this case 3D, same thing, memory address register 2001 4B, 2002 5C, 2003 3K. So now we are going to perform the write operation. So for write operation, the memory data register contains 3D. Now I want to write this data into 2003. This is what the write operation. In the memory location 2003, whatever the data available previously will be deleted. It is removed. Now I want to write. So what write? Already it is given in the memory data register 3D. This 3D is to be written into. That is why the direction is given like this. This 3D is going to 2003. Already 2003 contains 3K. Now write operation. Write operation means the previously stored data will be completely removed. The next one, the store operation transfers an item of information from the processor to memory. That is store. So store means write. Write means the data is to be written into the particular memory location. Destroying. So in the previous slide we have seen removing the old content, and then processor sends the address of the desired location to the memory together with the data to be written into that memory location. So with the memory location, the address of the memory will also be sent. Next one, instructions and instruction sequencing. So the task carried out by the program consists of, so normally a program means it is a sequence of steps, sequence of commands, such as adding two numbers, because now we are seeing the arithmetic calculation, so that arithmetic instructions are to be given in the program. So adding two numbers, testing for a particular condition. So particular condition means after completing the mathematical or arithmetic operation, is carry is appearing after performing the addition, or borrow is needed for performing the subtraction. So in this way, these like these two, there are so many overflow also there, signs are also there. So there are so many conditions for doing the after completion of the arithmetic operations. The conditions will appear finally. Those conditions are called as testing of the particular condition. That condition, what is the condition, that will be indicated by a register named as flag. So if we test those flag registers, then we will come to an idea of whether it is a positive number or negative number, or addition with carry, addition without carry, subtraction with borrow or without borrow. So these many conditions we will come to know. Reading a character from the keyboard, or sending a character to be displayed. So keyboard means through which we are giving the input. So displayed means to LCD or LED, the particular character will be displayed to others on a display screen. There are four operations. Number one, data transfer between memory and the processor registers. Data transfer between memory and processor registers. So in the processor also we could have some registers which are called storage registers, storage elements, but we should not call them as memory. Memory means it is external. Processor registers are default, which are inbuilt to the processor. And then second one, arithmetic and logic operation. So arithmetic means addition, subtraction, multiplication, division, and then logic operation means and, or, X are not, like, and so on. Then program sequencing and control. So sequencing means if it is performed continuously, program step 1, step 2, step 3 orderly, if these steps are executed, then it is okay. But in some program, the if or else conditions will be given. Suppose in the second, if the condition is given, if the answer is 0, then continue to the next step. If the answer is not 0, go to some other memory location will be given. At that time, the sequence of the program will be disturbed. That is why here program sequence of the program in which the execution is made is important. And then definitely the control is to transfer. That is why both are coming in the same sentence, program sequencing and control. And then IO transfer. So IO transfer means, IO means input output. So input means going into the processor, output means coming out from the processor. And then next one, register transfer notation. So how it is mentioned in the program, it is the transfer of information from one location in computer to another, one location to another location. And the second one, Possible location that may be involved in such transfers are memory location, processor register, or register in the IO subsystem. Definitely, these registers will belong to external devices because IO, so input and output both are external to the system. That is why in between memory to processor register or memory to IO or register to IO. That is what the meaning here. Next one, memory location may be given as LOC. So location instead of memory location, LOC it is mentioned. So location means it is memory location. Number will be given 2000 or 2001 like that. Next one, processor register, how it will. So memory location means the LOC. Processor register means R0, R1, R2 and so on. And IO register names may be because all are same only. The functions performed by memory, processor register, IO register are same only. But how same means what it is doing, they are saving the data, but the data saved by memory or processor register or IO register, how we will know? By mentioning in terms of words only. So for memory location means LOC will be given. For processor register means R0, R1 like that will be given. But in case of IO register, data in, out status, data out no. So data in means input, out status means output. So in this way, these three different words will indicate where the data is stored. And then R1 is, and then R1, see the arrow mark. This arrow mark will be like this also. See, the direction of the arrow mark indicates the transfer of data, but from which direction to which direction, from which location to which location, that is depending on the architecture of the system. So here we are doing R1. So location to R1. In this, actually we have to read location to R1. The data is transferred from memory location to processor register. In this way we have to read. See, means contents of memory location are transferred to processor register R1. This is what the meaning. And in the second statement, R3, here R1, R1 plus R2. R1, R2 are nothing but processor register only. So those two contents, R1 register content and R2 register content, are added together, and then the final result will be stored in the processor register R3. So all data storage will involve the processor only. So what is the meaning? Adds the content of R1 and R2, then places the sum, places the result in R3, overwriting the old content. So now the result is stored in R3, means whatever the content previously it is having, that will be removed. And then second one, assembly language notation. So move location comma R1. So this is the command, and what operation will be, what function will be performed when you give move location comma R1. And this statement does, it transfers from memory location LOC to processor register. So the content of location, memory location, will be moved or will be copied to the R1. So it is memory, it is processor register. So location to processor register R1. and the location contents are unchanged, because move means it is automatically equal to copying the data. That's all. Moving means not entirely taking from that. It is just copying the data. Move means it is almost equal to copying the data. It will not remove. So, okay. So here, from memory location LOC to processor register R1. Location contents are unchanged, but the old contents of R1 are overwritten. Like the previous case, here results are stored in R3 means the previous content is removed. In the same way, the location, memory location content is moved to R1 means this will be unchanged, but the content of R1, old content, will be overwritten. And then next example, add R1 R2 R3. It adds the contents in processor register R1 and R2 and then places the result in R3. See the data movement and the operation in this direction. These two contents are added and the result is stored in R3. So here R1 and R2 are added and result is stored in R3. So the direction is depending on the architecture only. But in some cases, normally in our microprocessor or microcontroller, what we will see, R2 content and R3 content will be added and the result will be stored in R1. So normally this is the way, but here in R1 and R2 are added, and that is based, both are correct, but the operation is based on the architecture only. So here the result is stored in R3. Next one, stack and queues. So stack. So in this lecture we are looking into the memory only. Starting from memory only, we are talking about memory and its data. So stack is nothing but it is only memory locations arranged in particular order, that is stack. So one over the another one, the memory locations are arranged and that is called as stacks. A computer program often needs to perform a particular subtask using a familiar subroutine structure. So we should differentiate. It is memory location only, but how the stack is differing from the ordinary memory location, because the stack is memory location only, but it will be used for special function. At what special function? When in the program, in the previous case sequencing, I told you, no, in between, suppose if or else condition is coming. Suppose in the first one, okay, in the second one, branching operation or conditional operation. If suppose 0, go to the next. If suppose 1, then go to some other memory location, I told you, no. So the control has to transfer to, if the condition is not satisfied, the control will go to some other location. Suppose it is to 2000 and it is 2001, 2, like that the program is written. And in the second line, the condition is not satisfied. The statement is saying that control should be moved to 3000. So 3000th memory location, the control will go, and then here some subroutine, a small task will be written here as code, and after performing this subroutine, it is main program, it is subroutine, and the subroutine should end with RET. So after RET, if it faces a RET, then automatically control ends the subroutine operation and goes back and resumes the original main program. And here it has to go to 3000, okay, because already it is stated in the program. While facing this RET instruction, the control has to go to 2002, and this 2002 memory address, it will forget. For that, before going to 3000 memory location, this 2002 will be stored in stack. After that, it will go to 3000. After seeing RET, the control will go to stack. It will take 2002 and then come back to 2002. So in this way, a special feature is seen for the stack memory location. For this special occasion, this stack memory operation is utilized. Next one, so to organize the control and information linkage between the main program and subroutine, a data structure called a stack is used. So this operation is explained now. Next one, a stack is a list of data elements, usually words or bytes, with the accessing restriction that elements can be added or removed at one end of the list only. So this is what the restriction given to stacks. But in queues, in both ways we can take the data. But in stack, one end is closed, one end is closed, one end is opened, and from this end we can put the data or we can take the data. This end we cannot disturb. That is what stated here, can be added or removed at one end of the list only. This end is called as top of the stack and the other end is called bottom. Bottom is closed. The structure is push down stack. And then another descriptive phrase, last in first out. So first in last out is another a stack operation, but in this last in first out stack. Why we are telling last in first out? Normally stack is a memory location and it will be so many location, but there is no need to have content in all memory locations. All, if suppose stacks are having 100 memory location, all locations no need to be filled in with the data. So whatever necessary, at least 50 locations can be filled. Maybe, or 60 memory locations may be filled with data. Remaining will be empty only. So I told you already that from the top only the data will be taken out or poured in. So one end is closed means and one over the another. So half only filled, remaining half not filled. Therefore, one register named as stack pointer will show the last one which is having the data. So here all are empty. So this one is filled in with the data, means this one is filled in data. So bottom locations are filled up with the data. This is the last location where the data is filled. Suppose if you want to take the data, this one only. So that is why last in first out. Whatever the last data, that will be taken out first. And after taking out, this stack pointer will go to the next location where the data is stored. And here also, if you want to take the data, this data will be taken because this becomes empty now. So that is why it is the operation is known as last in first out stack. It is it shows the description of storage mechanism. And so now second thing I told you, taken it, I told you that last data is taken out. So data is taken out means it is popping, we are taking out. Suppose if you want to put the data in, now it is last filled in, and this memory location is to be filled with some other data, means the data will come here, and this operation is push operation. So push means the data is inserted in, pop means the data is taken out. That is why the stack operations are there, are two stack operations, namely push and pop. We use stack that grows in the direction of decreasing memory address when new elements are pushed into the stack. So now what is the meaning? Pushed into the stack means now here data is filled. Now another, so that data pointer will be here, data pointer, because all are empty, this is data filled. Now one data is pushed into the stack means data is coming here, the stack pointer SP will move up. So in this direction it will move up. But the address will be decreasing. Address will be decreasing. What is the meaning? 0, 1, 2, 3. Now stack pointer moves up. You are pouring the data in. So moving up means 3 to 2. So this is the filled. This is the last filled data. So stack pointer from 3 to 2, it is moving up. So address is decreasing. Stack pointer is moving up and data is moving down. I mean return into, that is pushing the data into the stack. So the following figures show a stack of word data items at 43 bottom, minus 28 at top in the memory of the computer. Processor register is used to keep track of the address of the element. So what processor register? It is stack pointer only, and the stack that is at the top at any given time. This is called a stack pointer. Already I told you, stack pointer is nothing but it's a register, 8-bit register. And the diagram, it shows, see, in the see these are used, and this is bottom 43, top is minus 28. So current top element is minus, next one all are empty, but the address starts from top. So if it is moving up, then stack pointer memory address will be in decreasing order. Okay, right. So normal bottom element. So here previously I told you bottom element is containing 43 and top element is minus 28. Assuming these from here to here, we are using those memory locations as stack. Next one, queue. So next one, push operation, pop operation, how it is performed. Push operation, subtract equal that symbol, amber symbol, 4 hash 4 SP. Now what is the meaning? Why 4? Actually it is moving one location, but why we are giving 4? 0, 1, 2, 3. It for storing ASCII, it is divided into 4. So one first address, suppose first word. After that second word it should go, means the address starts with the 4. That is why subtract 4 it is given. Okay. So push means already the address will be decreasing. Decreasing means not 23 to 22, 21, not like that. At one memory location contains 4 ASCII words. That is why 4 memory location. So if it is decreasing by a word, means 4 memory location it is decreasing. That is what for push operation subtract 4. For pop operation add 4, because we are removing, means the stack pointer will come down and the address will be increasing order. So from top to bottom address increasing, from bottom to top address will be decreasing. So in the next see, so for pop operation add 4. This is what the difference. So if we are adding means move new item minus SP, because it is decreasing. No, that is why minus SP. Address decreasing minus SP. So here what is the pop operation can be implemented as move SP item, move stack pointer item, add 4. So SP count will be added by 4. These two instructions move the top value from the top into memory location item. So item is nothing but the memory location. So for memory location, the from the stack, the data value is moved to item which is named as memory location only, and then increment the stack by 4. Pop means add 4, so that it points to the new top element. If the processor has auto decrement and auto decrement addressing mode, then push means it can be performed by the single instruction move new in item. So push operation means minus SP. Pop operation means plus SP, no need to put plus in prefix plus, no need to put. But in push operation we need to put minus because it is decremented. No? So that is why minus SP. So in this up to this we conclude this video, and next video I will start from whatever I have concluded here. We will start in the next video. Thank you.